All right, so now it's time to talk about acids and bases. And this one to me is an incredibly crucial unit. In my estimation, students that understand acids and bases and equilibrium the best are those that are best positioned to earn a 5 or a 4 on the AP test. So I have a quote here from the fictional character Rocky Balboa. Every champion was once a contender that refused to give up. Again, there's a common theme that we're fighting all year. So that way at the end, we take out College Board. Like that's basically the game plan all along. So let's go in and go into acids and bases. And the first thing to recognize is that all a pH number does is it looks at the number of hydrogen ions to the number of hydroxide ions. And so when you have many more hydrogen ions, that's going to have a low pH. It'll be considered an acid. And you have a lot of hydroxide ions, it's going to be a high pH, and it'll be considered a base. So you can see here, high numbers of H plus ions are acids and low. High amount of OH are bases and low. And so where the pH scale comes from is that water goes through this process of autoionization. So you have H3O plus, which equals H plus. These are interchangeable. You can also call that a hydrogen ion and a hydronium, and then OH, it would be hydroxide. Every once in a while, two water molecules are going to collide together. And when that happens is the hydrogen on one is going to go on the other, and then you'll have H3O plus and OH minus. So when you look at the pH scale, what happens is that below 7 are always going to be acidic, above 7 are always going to be basic, and then the further from 7, the stronger the acid or base happens to be. And it's basically a range. So 6 is going to be less acidic than 2. 8 is going to be more basic or less basic than 15. So that's how that kind of goes. And then the other key component when it comes to pH is that one pH unit, it moves logarithmic. So one pH is actually 10x more acidic or more basic. So if the lake goes from a 5.9 to a 3.9, it's actually 100 times more acidic than it was previously. So to get you guys an idea on how logarithmic scales work and how quickly they can scale up or down accordingly, I basically have this analogy that I use where you use pH as if it were a room, and then basically length instead of pH number. So pH 7 were in my classroom, and pH 6 would be 1 meter away. 1 meter would actually put us in just 1 meter outside. So from my door, it'd be literally almost about halfway on the science hallway. pH 5 would be 10 meters away, which would put us in Prep's main hallway through Mr. Postel's room. So we're here. You can see there's 1 meter right there. There's 10 meters right here on the other side of Mr. Postel's room. pH 4 is going to be 100 meters. 100 meters from here going west will put us roughly along the side on Western by Hillside Elementary. pH 3, again, there was nothing, it's roughly 90th and Dodge, and there was nothing there, so I put a picture of that New Castle retirement community that's a little bit further south. pH 2 would be 10,000 meters away, which moving west would put you at roughly Boys Town. pH of 1 will actually put you roughly into Lincoln, Nebraska. So I posted a picture here of the Nebraska Stadium on game day. pH 0 would be 1 million meters away, and that would put you into Aspen, Colorado. And then pH of -1, if we keep going west, will actually put you in Tokyo, Japan. So basically from Omaha, that'd be about a 15-hour plane flight to get to Tokyo. So I hope this analogy was useful for you guys in determining how pH can move up or down very quickly when you compare this as meters. Many of you guys have seen this before. This is the pH map. And this map will help you when it comes to doing basic pH problems. So if you start from H plus and we're going to pH, you move along that line, you're going to take negative log of H3O. If you're going from POH to OH, you're going to go up this line. It'll be 10 to the negative POH power. If you're going from H plus to OH or vice versa, it's KW divided by H3O plus. And KW is 1.0 times 10 to the negative 14. And then pH to POH or vice versa is 14.0 minus the pH or the POH. So one thing I want to talk about is Bronsted-Lowry. The Bronsted-Lowry model has acids, which are H donors, and bases, which are H acceptors. And then a conjugate acid is a base that accepts H from the acid. A conjugate base, acid donates H to the base. And then your conjugate acid-base pair, you have an acid plus the conjugate base and a base plus the conjugate acid for that. So in a Bronsted-Lowry, everything's going to be matched up. So you have H plus, and it's going to be paired up with F minus. So this would be the acid. Once you lose that hydrogen there, you're going to have F minus, which is the conjugate base. In this example here, water is going to be our base because it's with this acid. So what's going to happen is the water is going to accept the hydrogen and become the conjugate acid. So base is always paired with conjugate acid. Acid's always paired with conjugate base. I wanted to give you guys another example. So we have NH3 with water. Again, water can act as either depending on what it's with. So on this first example, when we had an acid going into water, water acted as the base. But in this example, we have a base in water, so water is now going to act as the acid. So when water acts as an acid, it's going to give up the hydrogen. And when it gives up the hydrogen, it's going to go to NH4. And then what's going to happen is that then this becomes the conjugate base, and then this base becomes the conjugate acid. So I have 4 examples here. What I'd like you guys to do is pause the video and then try to set this up to get the acid conjugate base pairs. I'm going to go and show the first one actually. So I'll go and do A for you guys just so you have an idea what I'm asking for. Then I'll have you guys do B, C, and D by yourselves. So for A, we have NH4 plus and OH minus. What's going to happen is that NH4 plus is the acid. So what's going to happen is when this loses that hydrogen, this will be the NH3 will be the conjugate base. OH minus is going to be the base. And then when it reforms into water, that's going to be the conjugate acid. So what I'm asking you to do is to complete the equation and then identify the acid conjugate base and the base conjugate acid. And I would like you to do that for B, C, and D. So go ahead and pause the video, go ahead and work those out, and then start it, and I'll go through those examples. Okay. So for B, the deal is that HBr is an acid, so it's going to lose a hydrogen. So it become Br minus. And then water, H2O, is going to be the base, and so it's going to gain the hydrogen. So therefore, you're going to have H3O plus Br minus. So HBr is going to be the acid, Br minus will be the conjugate base, water is going to be the base, and H3O plus will be the conjugate acid for that. For C, what's going to happen is we have CO3, 2, and H2O. What's going to happen is that this is the base and this is the acid. So what's going to occur is that the hydrogen is going to leave this and it's going to go on to the carbonate. And then what's going to happen is you'll be left with HCO3 and the charge is going to go to -1 and OH minus. So carbonate, so CO3, 2 minus, and HCO3 minus are going to be base conjugate acid, and then the acid is going to be water. OH will be the conjugate base. For D, you actually could have gone 2 ways for this. I just show one of the 2. You could have basically, what I did is I chose to get rid of the H on the HSO4, but I know some students have gone the other way. Again, either would be acceptable. I'm just only showing one of the 2 potential solutions on this one. So HSO4 and water, So what's going to happen is this hydrogen is going to go in the water to be H3O plus, and then SO4 2 minus will be by itself. And then basically this is the acid and the conjugate base. This is the base and the conjugate acid. So again, make sure you know Bronsted-Lowry pairs, highly important, highly good. Though AP does not require you guys to recognize or know strong acids, strong bases, this is the list here that I would recommend if you know these. It's much easier to know these are the ones that are going to dissociate 100%. They're going to have really high K values and almost go completely to completion for that. Okay, so here's the water ionization I was talking about. So when water molecules come together, what's going to happen is every once in a while, two water molecules come together, and they will what's called auto-ionize, and one will become H3O plus, one will become OH minus. When you measure the concentrations of that, the H3O plus is 1.0 times 10 to the negative 7. The OH is also 1.0 times 10 to the negative 7. So Kw is 1 times 10 to the negative 14th power. And that is actually how we get a pH of 7, because in distilled water, perfectly distilled water, the hydrogen concentration is 1.0 times 10 to the negative 7. So that gets you a pH of 7. So here's our pH map again. And again, you use this to get along here. You'll use log, use 10 to the negative x power. 10 to the negative x power on your calculator should be located either right on or above the log key because they're inverse functions. So similar has addition, subtraction or inverse functions. Negative log and 10 to the x power are inverse functions. Either side on this is Kw, which is 1.0 times 10 to the negative 14, to make that function and make that work. So here is the items associated with the given sheet for the test. You can see all the items associated with K that they give you. Though they may have a separate acid-base one. I'll have to look at the new one, but everything on here is still going to be the same. So it gives you Ka, what you do to set that up, Kb, Kw, and it gives you the water constant. It tells you how to find pH. It tells you how to find POH. It tells you how to get that. This is the Henderson-Hasselbalch equation that we'll cover later on. And this one here talks about pKa and how to go from K to pKa or pKb from Kb. So you can see almost everything that I would ask you to know and memorize, you're provided on the given sheet. All right, so significant digits when it comes to log, these are not going to be tested, but I want to be incredibly accurate with this. The one key difference from how I've taught you significant digits is that when you actually have 3, like this has, it's not going to be 3 total digits, it's 3 behind the decimal point. So therefore, anytime you have a log, and you're doing negative log of 2.22 times the negative third, this 3 here will be 3 digits behind the decimal point, or 2.654 for that. So here I have some problems for you guys to do. These are 5 problems that using the pH map. So I'd like you guys to do is go ahead and pause the video, go ahead and give these 5 problems a shot, and then I will restart the video and go through these. These are basic ones you want to make sure that you have down and taken care of when it comes to this. Okay, here we go. So for number 1, what's the pH of an acid with an H plus of 3.0 times 10 to the negative 8? Well, pH is going to be negative log of 3 times 10 to the negative 8 molarity. So you have negative log of this, that'll get you a pH of 7.52. For number 2, what's the H3O of an acid with a pH of 8.5? We'll have 10 to the negative 8.5 power, so 10 to the negative 8.5 power will get us 3.2 times 10 to the negative 9th molarity. For number 3, what's the pOH of a base with an OH of 4.0 times 10 to the negative 6? Well, the pOH will equal negative log of OH minus. So pOH will equal negative log of 4.0 times 10 to the negative 6. Well, it'll get us a pOH of 5.40. What's the H plus of a base with an OH concentration of 4 times 10 to the negative 6? Again, what's going to happen? H plus is 1.0 times, KW is 1.0 times 10 to the negative 14. H plus will equal that divided by OH. So we have KW divided by that 4.0 times 10 to the negative 6. That'll get an H plus of 2.5 times 10 to the negative 9th. And the number 5 was a two-stepper. You basically want the pH of a base with an OH of 4.0 times 10 to the negative 6. So pOH will be negative log of OH to get 5.4. And then you'll take 14.0 minus the pOH you determined, which will get us an answer of 8.6. All right, good job on those. If you guys have any questions, make sure to come see me. Again, knowing how to do basic pH problems is useful. Usually on a multiple choice or free response question, they'll ask some type of basic pH question for that. Okay, so strong acids. Strong acids will dissociate completely or almost completely. So hydrochloric acid is a strong acid. You put that in water, it's almost going to break 99% apart to get H3O plus and Cl minus. And HCl is also called monoprotic, mono meaning one, protic meaning basically hydrogen to donate. So therefore, HCl will move into H plus and Cl minus. And it's important to know that the concentrations will stay the same. So you have 1.0 molarity of HCl. A lot of students want to make it out like, oh, well, I have only 0.5 molarity of H and 0.5 molarity of Cl. It's not true. Because each HCl molecule, when you break it apart, you have one hydrogen and one chlorine. If you have 1 molarity of HCl and you break it apart, you're going to have 1.0 molarity of H, 1.0 molarity of Cl, and you're good to go. So we'll go ahead and try this. Go ahead and try this real quick with the base, barium hydroxide, BaOH2, and let me know what you guys got for that. Okay, so we have 1.0 molarity of barium hydroxide, BaOH2. That's going to break apart to get 1.0 molarity. Ba will be 1.0. Because you're going to get 2 hydroxide ions, you'll basically have 1 times 2 to get 2.0 molarity of this. You need to make sure that you know how to do this. It's very common. They'll have different ratios like a 1-to-1, 1-to-2, 1-to-3. And then if you make this mistake here, it's really complicated or challenging to be able to get the answers correct for that. Okay, let's talk about neutralization. So neutralization reactions are strong acids and strong bases. We get water and salt. So you take hydrochloric acid and sodium hydroxide and mix them together. I want you guys to go ahead and try to complete that and then write the net ionic equation for that. So go ahead and try that and then restart the video, and I'll go through the answer on the next slide. Okay, so next slide. We have HCl and NHO3. Water's going to come off, so I'll have the H from the HCl, and I'll have the OH from the NaOH. And that'll give me water, and then what's left over is Na and Cl, so it'll be NaCl for that. And then a net ionic for that is I'm going to have H, I'm going to have OH minus, and then therefore we'll formulate water for that. And then we're good to go. If you have questions on this or confusion, make sure to let me know. Moving on to diprotic. So monoprotic donates 1 proton, diprotic donates 2. You don't need to know how to do diprotic equations. It's just important to know that when you have a diprotic acid, it'll deprotonate twice and give off a hydrogen twice. So sulfuric acid, H2SO4 plus water goes to H3O plus HSO4 minus. So what's going to happen is you'll have H2SO4 plus water goes to H3O plus and HSO4 minus. And then what's going to happen is the HSO4 minus will also get rid of a proton or hydrogen, and then you'll end up with this reaction here. I think it makes sense to use. You have mono and di, you can get tri. So phosphoric acid is the common one to have on triprotic. It is H3PO4 plus water goes to H3O plus and H2PO4 minus. Then the second one, you're basically going to get rid of this hydrogen here to go down to here, and the third one's here. So again, if you have 3 hydrogens to donate, it's going to be triprotic. If you have 2 to donate, it's going to be diprotic. And going back to our first, and I'm going back to the first one, it'll be monoprotic, as in the HCl for that. So we talked about strong acids. Now it's time to talk about weak acids. And weak acids is huge when it comes to acid-base chemistry. So acetic acid has the formula of CH3COOH. When you put acetic acid into water, it will break down, and you will have the hydrogen dropping from the acetic acid going to water to get H3O plus. But it's not going to be 100%. And so therefore, it's going to have an equilibrium. And so what happens is we need a Ka for that to happen. And that Ka for this equation here will be the H3O plus, which can be generalized as H. We have the acetate ion, which can be abbreviated as A minus, which stands for like what the conjugate item is or the item coming off. And then we have the original acid together, which is HA. And then, so therefore its Ka is going to equal concentration of H plus multiplied by concentration of A minus divided by concentration of HA. We covered K values before, so I'm going to go through this, but it's the same deal though. K is the acid constant. If the K value is greater than 1, it's going to be a strong acid. If it's less than 1, it's going to be a weak acid. I give 2 examples of 2 acids you guys are all familiar with. Hydrochloric acid has a Ka value of 1.3 times 10 to the 6th, so it's huge. And then acetic acid has a Ka value of 1.76 times 10 to the negative 5th, which is incredibly small. So I think you can see that all the hydrogen in hydrochloric acid is mostly going to dissociate, where very little of the hydrogen in acetic acid will dissociate. And you have to tackle acid-base problems differently to make that occur. So let's go ahead and look at that and see how that goes. So I have an equation here where our goal is to find, we're going to calculate the K of a weak acid at the initial concentration is 0.2 molarity, and the pH is 4.88. So we got to find the H plus concentration. This will be the first step. So because we have the pH of 4.88, we'll plug it into the pH map. So 10 to the negative 4.88 will get us an H plus of 1.32 times 10 to the negative 5th will be H plus. Then what's going to happen is, to help us with weak acids, we're going to use this thing called ice charts. And ice charts basically help you organize your data before you plug items into an equation to make that work. So from the problem given, we know that the starting amount of the concentration was 0.200 molarity. And so what's going to happen is, to set this up, you're going to have 0.22 molarity of acid. You're just sending it in, so none of it has disassociated. So H plus is going to be 0. A minus will also be 0. We know once it goes into solution, a certain amount of HA is going to break apart. So we're going to lose a certain amount of molarity of HA, and we'll gain a certain amount of molarity of H, and we'll gain a certain amount of molarity of A. And so in equilibrium, you'll have 0.22 0.200 minus x. This one's going to be 0, and then we're adding x, so it'll be x, and a minus will also be the same. So what's going to happen is when you plug this into the Ka equation, you'll have Ka equals H plus, so 1.32 times 10 to the negative fifth. And then you'll multiply that by the concentration of A, which is 1.32 times 10 to the negative fifth. And you'll divide that by the square root, you divide that by the concentration of the starting minus what comes off. Now, where the 1.32 times 10 to the negative fifth comes from our previous calculation here. Because we're given the pH, we can then find out the hydrogen concentration to make this go. So then when we plug this in and do all the mathematics for that, we're going to get 1.32 times 10 to the negative fifth molarity squared divided by 0.200 molarity. Then that'll give us a Ka value of 8.71 times 10 to the negative 10th molarity for that. So go ahead and try this one. It's very similar to the last one there, where basically if you start with 0.500 molarity of a weak acid, what's going with the Ka of 4.0 times 10 to the negative fourth, what will the H plus concentration of the solution be? So again, we have initial change equilibrium. Go and give this one a shot, and then I'll have the work on the next slide. So the initial will be 0.500 molarity. H plus will be 0, A minus will be 0. The change will be 0.500 molarity minus X. They'll have plus X and plus X. And then the equilibrium is that 0.500 minus X is going to be too small. So we don't need to worry about this. So you used to have to worry about doing what's called the quadratic equation when it comes to acid-base problems. They got rid of that. So by and large, if you set up an ice chart and it looks like you have to use quadratic, you don't have to do that because they've thrown it out of the curriculum. So you can always just assume that HA is just going to be too small. So then setting this up here, Ka will be H plus times A minus divided by HA. Again, since concentration of H equals concentration of A, we'll have H plus squared divided by HA. And because we have the K value is going to be 4.0 times 10 to the negative fourth, that'll equal H plus squared divided by 0.500. So when you are going to get H plus squared by itself, you're going to multiply this, and then to get H plus by itself, you're going to go and square root. So what's going to happen is you're going to go ahead and multiply 4.0 times 10 to the negative fourth times 0.500. That'll get you this value. When you square root it, you're going to get this value for H plus. So therefore, H plus for this one will be 1.4 times 10 to the negative second. Okay, so here is two practice problems to work on. Go ahead and pause the video, work on these two practice problems. I'll go through them. And then as always, if you guys have questions, you can let me know in class. Okay, so practice problem number 1. We have K of an acid of 6.5 times 10 to the negative fifth. Find the pH of the 0.35 molarity solution of this acid. Well, the K equals H plus squared over HA. And then we have 6.3 times 10 to the negative fifth will equal X squared over 0.35. When we manipulate and then solve for H plus, you're going to get 4.7 times 10 to the negative third. Then you're going to plug that into the pH. You'll have negative log 4.7 times 10 to the negative third. That'll get 2.33 will be the pH. For the second one here, we find the pH of a 0.275 molarity acid solution, whose Ka equals 3.0 times 10 to the negative eighth. Again, K is going to equal H plus squared divided by HA. We have the Ka. we have the initial concentration, so we're just solving for H plus. So you plug everything in, it'll look like this. And then when you want to get H plus by itself, it's going to look like this. We'll put that into negative log, and we'll get 4.04 for that. We've talked about Q and K, so this is just a repeat of that. Q is less than K, the reaction is going to shift to the right. If Q is greater than K, it's going to shift to the left. If Q equals K, then it's going to be at equilibrium. So we have 2NO plus 2H squared plus, and then goes in equilibrium with N2 plus 2H2O. This is what the K equation would look like since all these are gases. Same process works with acid and bases. A weak acid is going to have a Ka of less than 1. A strong acid is going to have a Ka of greater than 1. A base, weak bases, Kb's are less than 1. Strong bases, Kb's are greater than 1. So when you take acetic acid and you manipulate this, as we talked about, you'll end up with, when you have concentration of this, concentration of this, concentration of this, the Ka value will always be 1.76 times 10 to the negative fifth for that. Again, these are the equations that you will use. And again, this Ka value here can be put into what's called pK. So if you do negative log of this value here, that's going to get you the pK. So pK is negative log of Ka. And that tells you, okay, this is where that acid should be if it's at equilibrium at that particular point. So Kw of pure water, as I indicated, is 1.0 times 10 to the negative 14 at 25. It'll differ depending on where it's at. So, for instance, at 50 degrees Celsius, Kw is going to be 5.48 times 10 to the negative 14, and therefore the pH is going to be different. So, surprisingly enough, distilled or pure water at 50 degrees Celsius has a lower pH than it does at 25. And because, again, there's more collisions, and therefore you're going to have more autoionization of water, that's going to slightly temper it to a slightly lower pH for that. So Kw, if temp and K increase, pK has to decrease. So that process is going to happen. I'm going to show you this simple table demonstrating that. So we have temps of 0, 10, 25, 50, and 100. You can see here's the Kw values, here's the pK values, and these are going to be the different pH values that these items have. This just reviews again on weak acids and how to set up Ka equations. This is weak bases. So now we're going to talk about terms when it comes to making graphs when it comes to acid-base reactions. So it's important to really pin these down. So a half equivalence point is basically the pK for weak acid, or it's the half equivalence point is the pK for a weak base. And so the terms going from base to acid, the equivalence point is exactly enough base to neutralize all the acid. Half equivalence point is enough base to neutralize half the acid. End point is when the titration point where an indicator changes color. So on a basic acid-base curve, so this is an acid here. You can see because the starting pH is very low, close to 0. We're adding milliliters of NaOH to that. And then what's happening is it's going to move along, and then it's going to have this curve shape just like this. And what's going to happen is the equivalence point is 7, and you have equal concentrations. And what the equivalence point is enough. It's enough base to neutralize all the acid. So at the equivalence point, all the acid has been neutralized, and we're good to go. This here also adds half equivalence point. So what happens is that halfway on the graph when it's flat, is going to be half the acid is now gone. The equivalence point is going to be all the acid is now gone. And so when we do a titration, we have H plus HCl here, we have NaOH here, and then we have, in this case, we're using phenolphthalein. What happens is that the HCl is in here, the phenolphthalein in here, and then when you turn the acid to a little bit of a base, you're going to get a color change for phenolphthalein. You can use more than one indicator. So this graph here shows we have a base going to an acid, so we're adding HCl to that, or some other acid. The solution may start clear, then you're going to enter the phenolphthalein band right here, then it's going to clear out again, and then you'll hit methyl orange. So methyl orange changes colors in this pH range, phenolphthalein changes colors in this pH range, and this is where you can indicate that. Now, different atoms will get different graphs, and so it's important to recognize this. So you have a weak acid and a strong base. The initial point of the weak acid is here. You're going to have this buffer region where the half equivalence point is going to be reached. Then you're going to have the equivalence point where the pH is above 7, and then you'll end up with the strong base for that. So comparing a strong acid from a weak acid on these graphs, there's a couple things to indicate. Number one, the strong acid is going to start lower because it's going to have a lower pH. So in this case, this strong acid is a pH of 1. This weak acid is a pH of 3. On top of that, the strong acid is going to have more extremes. It's going to be very flat across. And it's going to have a massive rise up here and then flatten out the top. Where weak acids have a much stronger buffer region, so what's going to happen is as you increase the amount of NaOH, it's going to fight it a little bit more. So you're going to have this weird buffer region here as it's going to go slowly up. Finally, you're going to get to the point you're going to have an up slope, but much less. And then it's going to curve out again at the top, very similar to the strong acid. And again, what happens here, these are going to look very much the same because all the acid's gone. So at this point, you're just registering NaOH. Where here you're seeing the difference between the strong acid and the weak acid as it gets titrated across. It's important to know the different graphs. So strong acid was going into strong base like this. The pH of the strong base is going to drop. Strong acid with a weak base. Again, you have a weak base here and a strong acid. It's going to take time. You'll have that buffer region up here to go down. You have a weak acid and a strong base like this. Weak acid and weak base is going to look like this. So the amount of the acid that's going to be added for that to occur. So monoprotic acids. So again, acids in the FLAC, base is going to be in the burette. This is what this looks like. You go the other way, and bases in the flask and acid in the burettes can look like this. Diacritic like this, well, you'll have different midpoints or half equivalency points. So this is half equivalency point for 1, half equivalency point for 2. You'll have the first equivalence point and then the second equivalence point. And then for triprotic, you'll have first equivalence, second equivalence, and third. You'll have midpoint 1, midpoint 2, and midpoint 3. Let's go ahead and talk about Henderson-Hasselbalch equation. It's a tool to find pH of buffers if given. And so you're going to have the acid conjugate base or base conjugate acid. The equation's given on the equation sheet. So what's going to happen is you'll have pH equals pKa plus log over conjugate base acid. And then pH will equal pKa plus log A minus over HA. What will happen is that this is the equation set up here. We have the Ka value. I'm going to give you the concentrations of C2H3O2 is 0.20, and then of the C2H3O2 will be 0.50 for that. And then the question is, what is the pH? Well, we have the Henderson-Hasselbalch equation, so all I really do is just plug everything in. And so therefore, I'll have negative log of this because we know if we have Ka, we can get pK. The log of the A minus will be 0.50, and then the HA will be 0.20. When I do 0.5 divided by 0.2, that gives me 2.5. And then when I do negative log of 1.8 times 10 to the negative fifth, that gives me 4.7. Log of 2.5 is 0.4. So when I add those together, we're going to get a pH of 5.1. So here I have a different equation. I have slightly different items. I want to know what's the pH. Why don't you pause the video and then try to answer this one. Okay, so here's what's going to happen. pH is equals negative log of 1.8 times 10 to the negative fifth. Log is 0.20 molarity divided by 0.20 molarity. So you have negative log of 1.8 times 10 to the negative fifth plus log of 1. Log of 1 will add nothing to it. It's going to be 0. So it's going to be 4.7 plus 0 will be 4.7. Okay, now we're ready to do some advanced problems. Yes, bring it on. So what is the pH of a 0.20 molarity solution of acetic acid with a Ka of 1.8 times 10 to the negative fifth? Hence, you're going to need a net ionic equation, and you're going to need an ice chart. So go ahead and give this one a shot, and then I have the work on the next slides. Okay. So when you do the net ionic equation, the acetic acid is going to break apart to get H plus and C2H3O2 minus, and the Ka equation is going to be H plus, concentration of H plus multiplied by concentration of C2H3O2 divided by acetic acid for that. What's going to happen is the initial concentration is going to be 0.20. This is 0, this is 0. We have minus, we have plus, so that your equilibrium will look like this. Then what's going to happen is Ka will be H plus multiplied by C2H3O2 minus divided by HC2H3O2. You'll get 1.8 times 10 to the negative fifth will equal 8x squared divided by 0.20. When you manipulate that all through, x will equal 1.9 times 10 to the negative third. Negative log of 1.9 times 10 to the negative third is 2.7 for that. A 0.50 molarity solution of HCl has a pH of 1.13. What is Ka value? Hence, net ionic, ice, and then H3 plus value. So for this, we get the net ionic here. The Ka equation is here. Our H value is here. And so we'll have H to the negative 1.13 power to get 0.074 molarity. Then when you do the ice chart, we're starting off with this. This is the change. So we'll have this minus this to get that. And these are these items here. Then when you plug this into the Ka equation, you're going to get a Ka of 1.3 times 10 to the negative second. Okay, here is the next problem for this. We have 35 milliliters of 1.5 molarity HCN. Ka is going to be 6.2 times 10 to the negative 10th. It's mixed with 25.0 milliliters of 2.5 molarity KOH. What is the pH? Hint, net ionic, moles of reactants, ice, molarity of the solution, and pH. So this thing pretty much has everything. It's kind of like a kitchen sink problem. So go ahead and give this a shot. Go step by step. I think you guys can figure this out. I'll have the answers on the next slides. Okay. Net ionic is going to be this. HCN plus OH goes to CN minus in water. Then what's going to happen is to get this to set up, I know we have 1.5 molarity, so it'll be 1.5 moles over liters. We know we have 35 milliliters, so that's 0.035 liters. When we get that across, I'm going to have this many moles of HCN. I do the same thing for the KOH. I get 0.062 moles of that. Then I throw this into an ice chart. I have the initial moles over here. I have the change of moles over here. Again, because this is a 1-to-1 ratio, I know I'm going to run out of this first. That's why I make this. This is going to be all used up to get 0. So therefore, we're going to have 0.010 OH left. And this will be the concentration of the CN minus for that. So what's going to happen is I need to get molarity of the mixture. We'll have 35 milliliters of one, 25 milliliters of another. So the total amount's going to be 60 milliliters or 0.060 liters. Then to get the molarity of that, I'll take moles divided by liters, and the moles we have is this. So therefore, the molarity will be 0.17 molarity for that. Then what's going to happen is the OH is this. I can then use POH to get the OH minus. So the POH is going to be 0.76. So the pH of the solution is going to be 13.2. Again, all kinds of stuff loaded in there. But a good problem because it kind of covers a little bit of everything for that. Okay, let's go and talk about molar solubility or KSP problems. We covered some of this in equilibrium, but it's kind of good to touch this again. So we have lead 2 chloride has a KSP of 1.7 times 10 to the negative fifth. Again, low K value indicates it's going to be mostly tied up as lead 2 chloride. You're going to have very little lead ions and very little chlorine ions. So we need to find the molar solubility. We need to find out what mass of lead 2 chloride will dissolve in 4 liters of water, what volume of water is needed to dissolve the 5 grams. So what's going to happen is we've got to find the molar solubility. So KSP equals Pb2 plus and Cl minus. So KSP will be 1.7 times 10 to the negative fifth will equal X. And then we'll multiply that by 2x squared because we're going to get 2 chlorines to come off of this, and the chlorine's going to go up. So therefore, the ions will be there for that because we don't know what the concentration is. And then that'll be 1.7 times 10 to the negative fifth will equal 4x cubed. When you do the cube root, you get 1.6 times 10 to the negative second equals lead. Then you'll have 3.2 times 10 to the negative second molarity equals Cl for that. Then what's going to happen is we want to know what's the mass. So what's going to happen is we know that we have this many moles over liters. We know we have this many liters. We know that the molar mass of lead 2 chloride is this. So when you multiply and divide this through, you're going to get 18 grams is what's going to be in there. And then what volume of water is needed to dissolve? 5 grams. We have 5 grams. We divide by that. You're going to flip the molarity for that, and you would need 1.1 liters of solution to dissolve those 5 grams. All right. So, guys, as you can see, there's a lot of stuff in acid bases. We're going to piecemeal this together and make this be good to go. It'll be just a process we're going to work through as we get through this. So, again, let me know if you guys have any questions over any of this stuff. This is definitely a little bit more of a math-heavy unit with some concepts. But again, we will fight until the end when we test. All right, that's all I got. So good luck. Good work.